Circle review, number 43. I'm going to try to tap a little lighter because I noticed it was really annoying in the last video. All of them, it was quite loud. Alright, so each one of these blocks, there are 6 of them, are being pushed across a table at a constant speed. So again, V is constant, so that tells us that acceleration is 0. If it's a constant velocity, then you know there is no acceleration. By a force push of 1.3 newtons. What is the coefficient of kinetic friction? So mu k is what we are looking for. And the tabletop. So remember, mu s is when it hasn't moved yet, but it's about to move, and mu k is while it's in motion. Again, we're moving at a constant velocity, so not accelerating. That means that the forces are in balance. That is what Newton's first and second law of motion will both tell you. So let's solve with force vectors. So you've got the force push. I'm going to try to make it a little quicker so you can see these guys. Maybe this will work. So force push here. And then you will have this force. Well, I don't know why I did it so small. That was kind of silly. You're going to have a force push, force friction opposing that motion, the kinetic friction. Alright, so this situation is what we're going to look at, knowing that the force push is equal to 1.3 newtons, and we've got the kinetic friction is equal to force normal times mu k. We don't know mu k is what we're looking for, so I hope you ask yourselves, is there a way to find force normal? Because there are a few other forces. I'm gonna make this a little less thick, that was a little excessive. We're going to have a force weight that acts down and a force normal that acts straight up. Okay, force weight is going to be equal to 1, 2, 3, 4, 5, 6 newtons. So if you've got 6 newtons acting down, you must also have 6 newtons acting up for your force normal. So my kinetic friction is equal to, I know it's 6 newtons times mu k. But one thing we also know is that this kinetic friction is going to be equal to the force push. The reason being is because acceleration is 0. So if you really wanted to do it, you could sum the forces in the x and set them equal to mass times acceleration. Acceleration is 0, so you're going to set it equal to 0. The only two forces you have are the force push and a negative friction. If force push is 1.3 newtons, Sky, plus a negative k is equal to 0, add negative kinetic friction to both sides, and you get kinetic friction is 1.3 newtons that you can plug in here. Alright, I'm going to scratch those off so I can have a cleaner workspace here to finish this problem. Again, that's the reason that I know that I can set the kinetic friction equal to 1.3 newtons. It's equal to 6 newtons, my force normal, times mu k. So I'm just going to divide both sides by 6 newtons. Mu k is equal to 1.3 divided by 6. Which is, how many sig figs do we have? 2. Oh, we might actually have 1. Is that 6 newtons? Just 1? No, I think it's probably 6.0. Sorry, we have 2 sig figs. So 0.22. 0.22. And remember, Coefficient of frictions do not have a unit. So that was the answer to number 43. All right, I'm going to do number 44 as well because I kind of wonder if you guys just didn't get to it. Because if you struggled with those, 44 would also be a tricky one. So we've got a couch with a mass of, so mass of the couch is equal to, I'm going to change this back to 1. I'll make it a start bigger. Actually, please don't. 1.00 times 10 to the second kilograms. So that is 100 kilograms with 3 sig figs, however. So I should probably put it out there to remind myself. I'm being pushed, blah, 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 blah. No, that's the couch. All right, couch. Should have my pen off. On a ramp extend attached to a truck. So we've got a truck. Oh, I don't know why I always even imagine this at my truck. What do I do? All right, and there's a ramp. As one of the end of the ramp is raised, the couch begins to move downward. So I'm envisioning it being raised here to go up. So you've got the couch sitting on the ramp. What's going to happen is it's going to start moving down that ramp as that's raised up. We have a force weight acting down, which will be the mass of the couch times 9.81 meters per second squared, so 980 newtons, again with 3 sig figs. That's what we get for the force weight. Oop, 81, I don't know why I said 0. Okay. And then if the couch slides down the ramp, so acceleration is equal to 0.70 meters per second squared when theta is equal to 25.0 degrees. What is mu k? Please. All right. So this is the situation we have. These are the knowns we are given, and this is our visual. So I'm going to come down and draw my visual one more time with a little bit bigger, and probably on my next page here. I think that I can like just literally move it. Oh, I can. Okay. I'm not going to do that. I'm going to draw it down here. I want you to see the angles a little bit better. So let's assume that this is the platform. This is our couch. This is the ground, and they said that theta is 25 degrees. Remember how many sig figs, da, 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 da. Is it 25 or 25.0? 0.0. Okay, and we're gonna, I always draw a dot at the center of the mass. It just makes it easiest. And remember that the force weight's gonna be acting down. 981 newtons. Force normal is going to be, whoop, I'm drawing on its own to go straight there, is going to be drawn perpendicular to the plane the couch is sitting. I should put some lights on it so it looks like it's levitating. Alright, cute little couch. Alright, so this is my force normal. This is my force weight. But there are a few other forces in motion. So you need to kind of think a little bit to figure out which direction the frictional force is going. So if you are sliding this way, so that's the motion, the acceleration is in that direction, that means that friction is opposing that motion. So your frictional force is going to be right here. Okay, and it's in motion, so it's kinetic friction. They don't give us it, but we were given acceleration, and that was 0.70 meters per second squared. that's your indicator that we are definitely going to use Newton's second law, plus we pretty much use it on every problem. So that should also indicate that. So we're going to actually end up trying to sum the forces in the x and set it equal to mass times acceleration in the x, and possibly even sum the forces in the y and set it equal to mass times acceleration in the y. Let's start off with resolving our vectors. The reason you know you need to do that is because, yes, force normal and your frictional force are perpendicular to one another, but this force weight is not. So we need to get that guy resolved. I'll pick a different color so you can find my resolved vectors more easily. So my force weight. Again, I pick my axes based on which areas I have the most information about, and typically your x-axis is going to be where your motion is. So I'm going to draw my x-axis and my y-axis. Ooh, I think that was a sign that I draw too hard. All right. So y and x. Oh, I think that's up top there. So I was doing it too far up. All right. So now if you want to just orientate your paper like that to help you see it, the reason that this angle is going to be important is now we know that this is actually theta as well. So that would be our 25-degree angle. And your force weight is going to be your hypotenuse, and we're going to project it over onto the y and the x. So here's our y. So this is going to be my force weight of my y. Okay, and that's my adjacent. So utilizing SOHCAHTOA, I know that's going to be my cosine. So it's going to be cosine 25.0 degrees times my hypotenuse, which was 981 newtons. So my force weight of my y comes out to be 25 cosine 25 times 981 goes 889. Okay, so I got 889 newtons for my force and my y, and I'm gonna draw this in a different color just so you can see it. So again, this right here is my force weight of my y, and my force weight of my x. Whether you draw it here up on your x-axis, whichever one makes you see it better, but sometimes I like to see my triangle because you need that to be a right angle, and this is your theta. Okay, so that makes your force weight your hypotenuse. So my force weight in the x is going to be equal to the sine 25.0 degrees times my hypotenuse of 981 newtons. So force weight in the x, do a lot, don't I? Force weight in the x is equal to, my calculator, I'm going to type sine 25 times 981, 415 newtons. Alright, so we have our force weight in our y, our force weight in our x. So we have this guy. Trying to figure out how I'm going to show you that I'm talking about him here. I'll change colors again. So the summation of forces, we need to make sure that we've got each of these. So we've got our force weight in our x, which is this guy. And if you want to visualize it up here, he's right there. That's force weight in the x. Okay, and then we've got the frictional force. Those are your two forces in the x. So I'm going to sum my forces in my x. And what I have in the positive direction for this one is going to be the kinetic friction. And then I'm going to subtract or add a negative force weight in the x, which is 115 newtons. One other way we can do this is we could say that the motion is the positive direction. And if you did that, that should be fine as well. I'm actually going to do it that way. I think that's how the answer key did it, or that's why I don't know why I typically do it, but I do. That way you keep acceleration positive, I suppose. Okay, so I'm just going to say that the motion here is positive because it's going down away from the origin. So we're going to do force weight in the x plus a negative kinetic friction. Means the same thing, remember. So let's plug in the numbers and set that equal to mass times acceleration. Again, these are the only forces acting in the x direction. So my force weight in my x